Q&A session. And let me wait one more minute before saying it, but because I want to just start at 1 o'clock sharp. I should say 1 o'clock Edinburgh time. I don't know what time it is where you are, but okay, welcome everyone. We have a very exciting session of 6 ICALP track B papers to go through for this Q&A session. And we're going to start with the first paper on the list, which is on Skolem-hardness and saturation points in Markov decision processes. It's by Jakob Peribauer and Crystal Bayer, and Jakob is here to do the 2-minute presentation and then take questions. Jakob? Hello? Can Jakob hear me?
Yeah, but I hear you twice for some reason. Okay, but
Jakob?
Yeah, do you hear me?
Yes, we hear you.
Yeah, we hear you.
Okay, excellent. So let me.
Can Jakob hear me?
Yes, I can hear you.
So that's a very delayed signal you're getting, because I don't understand what's going on.
I guess someone has the YouTube stream running, and we hear the echo from YouTube.
Yeah, I don't have the YouTube stream running. So Jakob, if you have the YouTube stream running, do not run it.
Yeah, go on Zoom.
Jakob, are you okay to do your presentation, or
So, okay, I think now it's a bit better.
Okay, go ahead.
Okay, do you see my screen now?
Yes, we can see your screen.
Okay, excellent. So yeah, let me start by just very quickly summarizing what our paper was about. So the main contribution of the paper was a novel reduction from the positivity problem, which is related to the Skolem problem, to threshold problems in MDPs. And all these threshold problems come from a series of optimization problems, which are somewhat unrelated on first sight. On the one hand, we have variants of stochastic shortest path problems. And on the other hand, we have long-run notions concerning the satisfaction of path properties, long-run probabilities, and the logic frequency LTL. And for all of these problems, however, we also have a restricted version in which we can solve the optimization problem in exponential time, exploiting the existence of a saturation point, which further shows that the problems somehow share a lot of similarities. So let me maybe just show this overview over the results. So in the general setting, the threshold, the partial and conditional stochastic shortest path problem and the conditional value of risk are Skolem-hard if we allow integer weights, but the restricted version with non-negative weights is solvable in exponential time. And similarly for those long-run notions, as soon as we restrict ourselves to constrained reachability with A until B, we can exploit the existence of saturation points. But the general problem is Skolem-hard. So yeah, I guess I'm now happy to take questions.
Okay, I should mention we also have, in a sense, the kind of designated icebreakers that Michaela Klauch, who was, I don't know if she is here. If not, she might have posted a question on Slack, who in a sense was assigned to ask a question.
Correct, and I'm putting the questions onto the Zoom chat.
Joel, do you want me to read it, or would you like to read the question?
I think I'm happy to do either. It might be better if you read, because this way you can decide which ones to read and so on. And I'm concentrating on putting the questions, transferring the questions over.
Sure. Okay. So I'm trying to look at where have you put the
on the Zoom group chat?
Yeah.
So if you click on chat, you
yes,
should
I'm
see...
looking, and it says from Guillermo Perez. Is that the one?
Well, the one from Michaela is just below. It says from Michaela Clark.
I see. Okay, so let's just kind of start with the one from Michaela Clark, just to follow the procedure that as I was told. So it says, thanks for the nice talk. I have a question regarding slide 3. What exactly is the algorithmic approach for solving stochastic shortest path problems partially and conditionally?
Yeah. Okay. So maybe I just move to the slide where I explained the saturation point for because the idea for the partial and conditional stochastic shortest path problem, if we only have non-negative weights, is very similar. So in that case, we also compute a kind of saturation point. It is a bit more complicated than for the conditional value at risk. But the rough idea is that, for example, for the partial stochastic shortest path problem, if we accumulate a lot of weight along the path, then we don't want to risk anymore to not reach the goal, because then the path would be evaluated to weight 0. But then we really want to make sure to reach goal with as high a probability as possible. And actually, we can compute a bound, which depends on the minimal transition probabilities in the MDP and maximal weights and so on, which basically just tells us after how much weight we certainly have to make sure that we reach the goal at any cost. And so that is the saturation point. And from then on, we know that the optimal scheduler can just behave in a memoryless fashion, maximizing this probability to reach the goal. And once we know that, we can compute the values similarly to here, where we plug in some values at the level of the saturation point. And we also know the values when we reach goal, and in that way, essentially is also reduced to such a weighted reachability problem. And also for the conditional problem, it works in a very similar fashion.
Okay, maybe we can move to the next question. I hear an echo from my own speech, but I hope it's not too disturbing. So let me actually ask a question from Guillermo Perez. So it's the question is, he says, very cool and nice talk. Beyond mathematical hardness, have you considered improving the complexity lower bounds for the same problems? On the same note, what are the known lower bounds? So I suppose what this means, but kind of is, let's say for any standard complexity class, what is the best lower bound you have for, let's say, standard complexity classes for these problems?
Yeah, so that's a very good question, because of course the Skolem-hardness result doesn't approve any lower bounds, because I mean the Skolem problem is known to be NP hard, but that's it. So for the partial and conditional stochastic shortest path problem here, or already for non-negative weights, we know that the problems are p-space hard threshold problems. And for this constraint reachability and the long run probability, yeah, the threshold problem is NP hard. And yeah, of course, it would be nice to, let me maybe complete the picture. For the frequency LTI model checking of this very special form, the NP hardness result from constraint reachability should be easily transferred. And for the conditional value at risk, we don't know a lower bound at the moment, but I would guess it is also p-space hard probably. And yeah, I mean, our work doesn't help to improve these bounds, and we also don't know any results in this direction. And especially, we don't know any better bounds for the more general problems than for the restricted versions.
Okay, so thank you very much, Jakob. We're nearly out of time. Let me just see if there's a quick extra question. So,
can I? Oh.
Yeah, go ahead, Joel.
Oh yeah, so thanks for a nice talk. I mean, these problems are close to my heart. I guess two. One is a comment. I guess if you have positivity hard, you have you can improve the NP lower bound by you can show it's hard for the existential theory of the reals, which is a little bit of an improvement. I guess this is related to my question. You phrased the title and most of the work in terms of the Skolem-hardness. But of course, positivity hardness, which you also have, is stronger. And in fact, in your talk at some point, you say, well, it's unlikely that positivity, will be easy to solve because it would sort of, require some major breakthroughs in number theory. The same is not true for Skolem, right? Tomorrow, somebody could solve Skolem and it wouldn't really disturb the number theorists, but positivity it would. So I'm just wondering why you chose to phrase things in terms of Skolem when positivity it seems to be a much bigger obstacle on the face of it.
Yeah, that's actually a good question. And well, I think the main reason, maybe especially why in the title we didn't write positivity hardness, is we had the feeling that positivity hardness, if you just hear the phrase out of nowhere, doesn't really lead you into the mindset of the correct problem, while maybe the name Skolem problem is just more prominent. But yeah, you're absolutely right. All our results are positivity hardness results. But there's maybe an important point here. And yeah, we try to make that clear in the paper then, but for the title we decided to go with Skolem-hardness maybe. So,
okay, thank you. Thank you, Jakob. I think it's time to move on to the next paper because we've already passed our 10-minute threshold. So thank you very much. The next paper is Bisimulation equivalence of pushdown automata is Ackermann-Complete. I believe it's sorry, I'm looking for Wenbo Zhang. Would you like to do your 2-minute presentation for your paper, and then we can have questions for it?
Okay.
We don't yet see your video.
Can you see my slide?
Yes.
Okay. I will give a brief introduction to our work. An important problem in theoretical computer science is to decide whether two systems behave equivalently. And Bisimulation equivalence plays a central role among the many notions of equivalence relations. The Bisimulation equivalence of pushdown automata is an important problem in the area of verification. Given two configurations of PDA, the problem asks if they are equal in the sense of bisimilarity. Sandy show that the problem is decidable, and last year Yangsha and Schmidt showed that the problem is in Ackermann. I'm sorry if I mispronounce anyone's name. We improved the lower bound from the elementary to Ackermann-hard and closed the complexity gap. It is proven by a reduction from the coverability problem of reset patronite. It's similar with the proof of the Ackermann-hardness on the bisimilarity for first-order grammar. We modified the proof by Yangsha by avoiding introducing internal transitions. We also give a parametric complexity on the problem. When the number of control states is fixed as D and D is greater than 4, the problem is FD minus 1 hard, and it is a complexity between elementary and primitive recursive. And our results can be generalized to normed PDA. And so the bisimilarity of normed PDA is also Ackermann-Complete. Okay, that's all. Thank you for your interest.
Okay, thank you very much, Wenbo. And now it's time for questions. If somebody either would like to raise their hand, or else I'll ask if Joel could.
I think Felix has proposed a question. He's willing to ask it verbally.
Yes. So you show a reduction that is mostly polynomial, and then you have that one exponential time thing in the initialization. And you mentioned that there is a fix for this in the paper. Now, I didn't read the paper. Could you quickly summarize how you turn that into a polytime reduction?
It's a well-known technique. It's so you can use the stack symbol to encode binary numbers. It's very similar with formal works.
Mm-hmm. Thanks.
So for example, you can have some stack symbol A1, A2, A3, and from A1 you can do an action to A2, and from A2 you can do an action to A3, and so you can you can encode a binary number in the stack
Mm-hmm. Makes sense. Thanks.
Okay, thank you. Any other questions? Anybody who would like to bring in? Well, if there aren't any other questions for now, what we can do is kind of move on to the next paper, and we can actually come back later if people, at the end, if people have questions about earlier papers, we can kind of return to them. Okay. Thank you very much, Wenbo. And so now we'll move on to the next paper on polynomial recursive sequences, which is being presented by Filip Mazowiecki.
Thanks.
Mazowiecki, sorry, apologies, yeah.
I cannot share the screen.
Just a second. Okay, now you should be able to. Sorry.
All right. Okay. So I will make a short presentation of our result. Since I don't have much time, I prepared a shorter version of my slides. And the paper is essentially about a class of sequences, which can be defined by, you have a system of sequences. So here you have two sequences, A and B. And the word polynomial refers to that when you recursively update the value of the sequence, it's not only linear, you can also use multiplication. So here's a typical example that you can define n factorial like this. Just multiply every time the previous value by n. So second example, if people know vector addition systems, it's a well-known example that every time you just need one sequence for this, and every time you square the value, then you get a sequence 2 to power 2 to power n. So the main problem we were looking at is, can you express a particular sequence n to power n like this? And our main theorem can be summarized in one word, no. And we have some corollaries from this about weighted automata. And that's the end of the presentation.
Okay, thanks very much. So we have some questions. I'll start with a question from Guillermo Perez. And the question is, do you know if there are other extensions of weighted automata which may potentially contain all classes from slide 13?
I don't remember what is really slide 13.
Okay.
But yeah, I know what he refers to. There are like three. I guess he's referring to that there are three extensions of weighted automata. And one of them is biologic, one of them is essentially like this polynomial recursive sequence, and one of them is like with context-free grammars. So my short answer is no. I mean, there is no natural extension that covers all of them, but not that I'm aware of. They are completely different in nature.
Okay. Thanks. I think let's go to the next question. This is, I guess this is directly from, oh no, sorry, it's from Shal Almagor, and it says we could consider tropical polynomial sequences where the operators are kind of the max plus algebra instead of plus and times. Can you say anything about such a setting?
Yes, so this is actually a good question because actually it's a problem I'm working on. So one could like you can rephrase this question. I will not go into technical details why, but essentially you can consider linear recursive sequences. So if like it's like this class, but you don't allow for multiplication, but instead you allow to use the operation of taking a minimum. And this is like a polynomial recursive sequence in the setting of the tropical semiring. And so what I expected is that this class could collapse into just that you can just as well not use min, and this is what I expected. But then actually Joel showed me a counterexample that if you can actually take a minimum of two linear recursive sequences, which cannot be expressed by a linear recursive sequence. So in a way, it's different, but I still think in some way this class can collapse, but it's more technical to explain. So that's the answer.
Thank you.
Okay. Sorry, may I just ask for clarification on that? When you say you still think it can collapse to what? Because you've just indicated that it doesn't collapse to just linear. So yeah. What do you mean by that?
I mean that collapse to, because when you allow to use the minimum operator, you can put it anywhere. I think it can collapse that you can use that to the class of sequences that you have a minimum of a fixed number of linear recursive sequences.
Okay. Thanks. Okay. Next question is from Thomas Webster. It says, are there any results known about inclusions or lack thereof between weighted MSOs and weighted context-free grammars? For instance, is Catalan known to be in weighted MSO?
I don't know. I think the answer is that it's not known, and I would expect that they're incomparable. But this is a difficult question because the problem with weighted MSO is that among all the three extensions, it's the only extension for which it's hard to come up with a natural equivalent class of sequences. So my answer is I don't know, but I conjecture that there are different classes.
Okay. Any other questions? Anybody want to? Joel, I think your mic is,
Yeah, sorry, I just unmuted. So I guess just a quick question / comment. So I guess in the definition of the polynomial recursive sequences, you allow the coefficients are constant. Is that correct, Philip?
What?
The coefficients are constant, meaning they cannot depend on n.
Yes, but you can add n easily in this class.
I see. So it's if you were to add polynomial coefficients, it wouldn't actually change the expressiveness of that class.
It's because you can define polynomials, and then this class is
of course. I see. Okay. Yeah. Thanks.
Any other questions? Okay, again, it seems there's no other questions for now, but at the end of the session, if we still have remaining time, we'll be happy to revisit any of the papers in the session. So I suggest that we move on now to the next paper in the session, which is on decidability of time-bounded reachability in CTMDPs. And I think the presenter is Mahmoud Salamati.
Yes. Hi. Let me share my screen. So I guess that you should be able to see my screen, right?
Yes.
Okay, so I'm very glad that our paper has gotten in ICALP 2020. And in this paper, we consider an important and well-known class of continuous time stochastic models, namely continuous time Markov decision processes. And we study decidability of time-bounded reachability problems for this class of models. And it's known that this decidability of time-bounded reachability problem for continuous time Markov decision processes is open. Our main contribution is that we show that this problem is decidable subject to Shanwell's conjecture. So this is our main result. And another result is that we consider a related problem, namely to check whether a time-bounded reachability problem has a stationary optimal policy or not. And we show first that this problem is decidable subject to Shanwell's conjecture. And furthermore, we show that this problem is a Skolem-hard. Therefore, it's not likely that one can prove its decidability unconditionally. Yeah, it was very brief, and thanks. I would be happy to take your questions.
Okay, thank you very much. We have a question from Michaela Klauk, and she says, thank you very much for an interesting talk. On slide 9, I wonder how is the exponential polynomial associated with a policy calculated? I guess only with the constraint that at the switch points there has to be a non-tangential zero. The polynomial is not uniquely defined. Is this true? If so, is it correct that for the following calculation, it is not relevant which of the polynomials is chosen as long as the switch points are non-tangential zeros?
Yeah, so it's a very long question. So is this the question that I answered already, or is it different? Let me check you.
When you say you answered, you might have answered it on Slack, but we don't see.
I don't see anything on Slack, and I'm not monitoring YouTube.
Okay.
It's in the other thread on Slack. It's in the thread for my talk.
Oh.
I see.
Oh, okay. Sorry.
Okay, well, I've moved on. I've moved on from your talk, I'm afraid. So you just have to answer it again.
Okay. So the thing is that the way that we count switch points, we start from the case that we don't know whether we have a switch point, the optimal policy has any switch point or not. We examine the exponential polynomial and we know exactly which exponential polynomial to consider. And then once we found the first switch point, we just move into the next switch point. And this way we know exactly which exponential polynomials should we consider.
Okay. Any other? I see. Now Joel has put your reply into the chat. Okay, thanks, Joel.
Thank you, Joel.
Any other questions? any other questions? So, so perhaps I can kind of ask a question here. Just so, do you do you have any results to the effect that some of these things that you've shown, their requirement of Shanuel's conjecture is sort of essential in the sense that if you were able to avoid some major number theoretic conjecture like that, and still establish the same, unconditionally establish those results, that there would be some breakthrough in number theory or something of that sort. Do you understand what I'm saying?
So this problem, so the way that we propose our decidability result, we use decidability of first order theory when it's augmented with exponentials and sine and cosine over bounded interval, and therefore we needed Shanuel's conjecture.
No, but can you actually encode the first order theory with exponentiation in your problem in such a way that would then allow you to say, well, it's inevitable to use Shanuel's conjecture or something that will give you kind of the decidability of the theory of reals with exponentiation?
So if that happens, it would be, I think it requires some important advances in number theoretical aspects of.
No, I'm talking about the result about continuous time Markov decision processes. I'm asking,
yes,
you've shown that you can basically boil things down to decision problems associated with the first order theory of reals with exponentiation, and therefore using Shanuel's conjecture you get decidability. I'm asking, can you also show that it's essential to, in other words, can you encode let's say a first order this sort of statement in the theory of reals with exponentiation as an instance of your problem about CTMDPs? So if you were able to do that, then you would be able to say that I actually need Shanuel's conjecture.
No, that we haven't tried. So if that happens, then we can say that it's two-sided, this relation, and therefore, so no, we don't have such result. I mean, but it's a very interesting question. But I don't know answer to it.
Okay, thanks.
Sure.
There's a couple of new messages. Sorry. I didn't catch those before. So so
I can pose one live.
Yeah. Okay. Good. Yeah. Thank you.
I dumped it in Slack. So this is, I think, is a very, very nice result. I do think it closes somehow up to the conjecture. It closes this question. Now, everyone out there who works with CTMDPs and time-bounded reachability does approximation. They have an approximation algorithm, basically. Any implications for the approximability that follows from your results, or is this entirely independent?
So these approximation schemes should work in most of the cases, but so the problem occurs when the corresponding exponential polynomials have tangential zeros, and this is this is what makes the problem hard. If such a thing happens, those numerical approaches would be likely to be broken, and that's the main case that.
Okay, so you have some kind of toxic examples, so to speak, where one can now see how the approximation algorithms behave, because your conjecture is that they don't behave well.
So yes, I mean, but we haven't brought this into our paper, but yes, there are. We had this example that was quite. A number of states was not too small in order to bring it into the paper, but yes, we figured out that this thing can happen, and that is the case that these numerical approaches could fail. In most of the cases, they won't fail, but yeah.
Okay, nice. Thank you.
If I could ask a quick follow-up question to that. You said that the real problem comes up when there are these tangential zeros, but does it really need to be actually a tangential zero for it to be a problem? Or is it sufficient for it to be darn close to being a tangential zero for it to already be a problem for the approximation? Do you see what I mean? Like something could be so close to being a tangential zero that you could hardly tell the difference without zeroing in on it sort of double exponentially.
So if you know that this tangential zero doesn't occur, everything is fine. But if there's, so let's say that there you could somehow figure out that for these nice stochastic models, tangential zero doesn't occur for corresponding exponential polynomials, and in that case, yes, everything would be so we could get very close to this tangential behavior, but because we know that there is no this tangential zero would not happen, then we can use this numerical approximation and just keep reducing the step size until we find out this zeros. But
the problem is you don't know how accurately you would have to do that before you can be sure.
So that's why I'm saying that if you were sure that because of some properties of the system, of the model, you cannot have this tangential zeros, then you could give a numerical approach. But in this case, you can't. You can't exclude such case, and therefore, it becomes a hard problem.
Yeah. What you said is still not completely clear to me, but I think I'll take it offline because I think,
sure.
Yeah, okay.
Sure.
Any other questions?
There's one more question I put into the chat from Slack from Stefan Kiefer. Sorry, I didn't write it was from Stefan Kiefer, but this one, when it says, did I understand correctly? Let me read it out.
Yeah.
Did I understand correctly that you don't have a hardness result for the time-bounded reachability problem for CTMDPs? It seemed that the hardness results are all about a stationary optimal policy.
Yes, the hardness result is about whether it's correct. This is
yeah. So I think you somehow, this clears the confusion from earlier. There was yeah. So answering Stefan.
Okay. Yeah. Great. Thanks, Joel. Okay. So I think we can now thanks very much. We can now move on to the next paper. It's on the size of finite rational matrix semigroups with a number of co-authors, but the presenter is Jonathan Tanner. Jonathan, your microphone is muted.
Sorry. Hello. Can you see this?
Yeah. Yes, we can see your slide. Yeah.
Brilliant. So we're looking at these structured semigroups where we take a number of matrices and multiply them together in all the possible ways. And we're only interested in cases where the resulting semigroup is finite. So here is a small example. We then define the length of an element in that semigroup to be the length of the smallest product that produces that element. Yeah. And then we bound the length of that. And so our result is a length bound for rational finite matrix semigroups, which does not depend on the number of generators and is, well, the length is singly exponential, which gives us a doubly exponential size bound. Prior results were non-elementary. Brilliant.
Okay. Well, that was short and sweet.
Sorry.
Okay. No, that's good. That was not a criticism. If that's all that you wanted to say. I was also quite amused by that little bit in your talk where you said that, so the actual result value is 3 and the upper bound we get is 2 million something or other. And you said, yep, so it's very close.
Yeah,
I think it was 28 million.
Yeah, in this case, it's 28,311,552.
Yeah.
It is still exponential.
Yeah. But yeah, very that was charming. So, okay, question. Let's move to questions. And there's a question from Pengfei Yang and says, "Thanks for your interesting presentation. I have a question for you. You mentioned that the results do not hold for real matrix semigroups. How does it illustrate in the proof?" I suppose what he's asking is, where exactly does your proof break down for the kind of real semigroups? You give an example in your talk that it just shows, rotation is itself already kind of going to give you unbounded. But the question, I suppose, is what actually fails in your proof?
These rotations. This is actually an unbounded group. And so this also illustrates that the group case breaks down. And so while our proof doesn't depend on we don't actually look at what's in the generators, the bounding comes by effectively reducing it to the group case. So if the group case is unbounded, then we have no bound. But I don't, as far as I can remember, there is no actual thing in our proof that is actually doing anything with these matrices other than looking at their kernel and image.
Okay, I don't see other questions. So you mentioned in your talk that there's kind of, for the group case, there's this polynomial time algorithm from Babai et al. About kind of determining whether the thing is bounded in the first place, like this. That's the decision question that is polynomial time, but you do not know that for the semigroup case. So do you imagine that some of the techniques there would translate to the semigroup case, or kind of, in other words, what fails in trying to translate the results from Babai et al. To the semigroup case?
So I'm not really familiar with those, with how they proved that. They used, I believe they used a quite different method to the one based on, so here we're sort of taking our length bound, producing a size bound, and then brute forcing it. And you can do the same thing for groups, but I think to get their stronger polynomial decidability result, they had to approach the problem quite differently. So I haven't looked into how they did that. It's possible that similar results may work, but
yeah. So it's go ahead.
Sorry. I think one of the sources of exponentiality is from when you're using these graphs where you're bounding the length of these, when you construct this reachability graph, and that uses algorithms for the group case as a black box, right? I mean, the handling, you somehow reduce the semigroup case to the group case by, this sort of complicated this complicated construction where you somehow induct on the rank and so on. But so the idea of going from a group case to semigroup case, most of the difficulty is somehow reducing from semigroup case to group case, and this you already get an exponential blow up in doing that. Yeah. If that answers your question, Kusha.
Well, I guess in a sense the Babai result has to somehow avoid the exponential blow up even in the group case, right? So my understanding is even in the group case, there's an exponential blow up for these kind of lengths, etc. Yeah. So that's not, they have already circumvented that somehow to get a polynomial time algorithm. So, maybe the same thing can be done in this setting. And that's I guess the gist of my question is,
it's entirely possible. I haven't looked into how they did that.
Okay. Okay, so that's encouraging for the young folks in the audience who want a problem that hasn't fully been tapped, to kind of try to, since the authors are saying they haven't yet thoroughly investigated this. Sorry.
I think it's listed in our open problems at the end here.
Yeah, exactly. Yeah, but it's sort of, how should I put it? It's sort of encouraging to know that you haven't yet fully investigated the prior work to see whether it could be translated to this setting. But, okay. Any other questions? Okay, so if not, then thank you very much. And we will kind of, again, we'll move on now to the last, paper in this Q&A session. But if there are remaining questions about earlier papers, we will come back to them. So do not leave if, that's what your intention is. So, okay, the final paper in this quick Q&A session is Invariants for Continuous Linear Dynamical Systems, and it's by a number of co-authors, and the presenter is Shaul Almagor.
Thank you very much. Yeah, so this paper is about invariants for continuous linear dynamical systems. If you've seen the video, you're likely to remember it. I'm not going to play the whole thing, and I don't have slides because I have video. So just jump to the main point, or one of the main points. And that is the following. Right. So what we do is look at continuous linear dynamical systems. And these are characterized by these spiraling orbits. You can think of them as spiraling orbits. And what we study is invariants for these systems. An invariant is a set that contains the entire orbit or some of the orbit and is itself invariant under the dynamics of the system. And we study this in the context of reachability. So we have also a target set, and we want to look at whether the orbit intersects the target. And to handle that, we want to find an invariant that is disjoint from the target, and that would prove that we don't hit the target. And what we show is that invariants can be characterized by these cone shapes. And what we prove specifically is that if you have some O-minimal invariant, or think of it as either a semi-algebraic invariant or an Rx definable invariant, then it must contain this entire cone thing from some height. And let me jump to the results for a second. This is not what I wanted to do. Yeah. So what we show is that we can characterize invariants or minimal invariants with these cones. And if the targets we look at are definable in the theory of the reals with exponentiation, then we have conditional decidability with Shaniel's conjecture for the question of whether there exists an invariant that is disjoint from the target. And for semi-algebraic targets, we have unconditional decidability when the target is semi-algebraic. And this is only for eventual invariants, so not invariants that contain the entire orbit, but only from some height and on. And we show the existence of semi-algebraic invariants whenever the target is semi-algebraic. So even though the cones themselves are not semi-algebraic, we can approximate them using those fat cones. And these are also for eventual invariants. And for the complete invariant, for an invariant that contains the entire orbit, we show hardness for positivity of bounded time, or hardness for some problem that is kind of open, which I will not go into unless there are questions about it. That's it.
Okay, thank you very much. So let's try to go for questions. I don't. Oh, I see now. I see a question. So there's a question from Philip is saying, "Is your problem the point updates are in your problem? The points are updates. The point updates are defined by a matrix. If the updates are nonlinear, for example, defined by polynomial maps, do you have any undecidability results?"
Yeah, I'm not entirely surprised by this question, but so yeah, the question is basically if we replace the matrix with, instead of linear entries to polynomial entries, what would happen? We haven't looked at it in the paper. Essentially, if you have polynomial dynamics, then the problem becomes a lot harder, and most things become undecidable. There is a paper by Emmanuel Henry, which I think is here, that shows that most things become undecidable because basically you can simulate a Turing machine. So I suspect that everything will be undecidable in this context as well, but we haven't looked at the details. So there is a slight hope, but I wouldn't count on it.
Mm-hmm. Any other questions? So I would actually like to ask you about the almost hardness result that you suggested. So I actually wanted to understand why you feel that that's a hard problem, because normally, I mean, I've seen a number of results about kind of diagonalizable cases where things are significantly easier and you can get decidability. So I was just wondering why that particular case with that in that diagonalizable setting you believe to be hard. Maybe you can elaborate on that.
So the fact that we have a diagonal matrix is, so we reduce from hardness of a special sum of exponentials, which can be described as a diagonal, as an exponential of a matrix, of a diagonal matrix with real eigenvalues. The fact that the matrix is diagonal is not too worrying. It's still very, very hard. It's still a very, very hard problem because the dimension is unbounded. So you can have all these intricate relations between the eigenvalues.
Yeah, sorry, I meant diagonalizable and real. So
yeah. So the real thing, well, technically, we don't know how to solve this problem, so we consider it hard. But there is evidence that it's been looked at. So the paper, I think it's by Paul Bell, the paper that studies this states that the problem is open when the matrix is not real, kind of demonstrates that the hard part doesn't go away if you have only real entries. I can't say exactly why that is. Maybe Joel has a better answer for that, but it seems to kind of maintain the hard bit. Maybe I wouldn't count on these problems to be interreducible, but it still seems hard enough.
Okay. Any other questions about this paper? Okay. If not, we can sort of open the floor to any questions about prior papers, or sort of, I also perhaps have a sort of a question that kind of interconnects several of these papers, at least two of them, and perhaps even a little bit more, is like sort of some of the results that have been mentioned. I mean, the kind of hardness results that are kind of relied on are you know, kind of hardness for the Skolem problem or positivity, etc. And I understand, and of course, I know of some of the work by Joel and Worrell that establishes connections between these problems and difficult number theoretic problems. But what I wanted to understand is, do we not at least have a candidate algorithm for these problems already? Namely, this is a question actually. So for both the Skolem problem and the positivity problem, as far as I know, we do not know a family of examples that would show that, let's say, iterating exponentially in the encoding size of the input matrix is not sufficient to know whether or not, so I don't know what the exact exponent one should try would be, but let's say just single exponential number of iterations for the sort of standard linear dynamical system problem. Let's just say, I'm talking about the discrete case now. It seems sufficient that like a single exponential number of iterations could be sufficient to discover, let's say, a zero, or discover non-positivity if that were to exist. We don't seem to have any counterexamples to that. Is that a correct statement? For both Skolem and positivity?
As far as I know, this is correct, Kusha. I think, and if not single exponential, and certainly double exponential, but we don't have families of examples of tricky things. I mean, these things are extremely hard to build, obviously, because you would have to, I mean, yeah, coming up with a family of examples. But I think you're right. We don't have any, but at the same time, I don't know if there are good reasons to believe that they don't exist. I just don't know.
Yeah, I mean, I guess the point I'm trying to make is that unlike other hardness kind of things, here it's a problem where we actually have an algorithm that, for all we know, works perfectly fine. In other words, you know, it's, you know, whereas, for example, I don't know, if you prove something that, you know, something is like Turing hard, obviously you don't have an algorithm that you know works, you know, because, you know, you have the halting problem, and, you know, sort of like, so, yeah. Okay, that's just kind of a minor point that I wanted to say. Okay. Okay, I'm trying to see if there's, so I should let others chime in now. Anybody want to say anything about any specific paper that you have a question about, or general comments that might relate them?
There is, sorry, I just noticed that somebody just posted, Stefan Kiefer just wrote on the chat. Perhaps I can read this.
I see it. Yeah. Okay. Thanks.
Go ahead.
So it says there are subclasses. So this is a question for Wenbo Zhang. The question is, there are subclasses of PDA, for example, PDA with a single control state, where bisimulation equivalence has elementary complexity, but there's still a complexity gap. Are you working on closing these gaps?
Yes. Yes, I am working on it. And Yangcha has proved that the bisimilarity of OCN when the counter is encoded in binary is EXP space hard, and I want to use the idea in the proof to generalize to the PDA, and I'm now working on it. I have some idea, but I have not complete it. It's a very good question, and have many things want to share, and I will.
Just to clarify, when you said OCN, you meant one counter nets? Is that what you meant?
One counter net, yes, one counter net, and the counter is encoded in binary, and the problem is EXP space hard, and now the PDA with a single control state, it is EXP time hard, and the upper bound is 2XP time. I'm now working on the problem. I'm working on the bisimilarity of BPA.
Okay, great. Thanks. Okay. Any other questions or comments? Well, if not, thank you very much both for the speakers for their presentations and their kind of Q&A, and thanks very much for everybody who participated, and we will see you at other online events during ICALP, and take care. Bye.
Thank you.
Thank you.
Thanks. Bye-bye.
Bye.